So let's actually do something else. Let's actually invent the formula. So I'll leave number 1 as a practice problem for you, but I'm going to use this space to actually create that formula. It's kind of a cool relationship. The idea would be that if I wanted to find, and I guess paying attention is optional. I don't know when that became a thing, but this is essentially the meat of the expression. Because if we could figure out what this is, because that's what the denominator is really talking about. Yeah.
Is that like second derivative?
No, it's actually the derivative of an inverse. So.
Oh, yeah.
But yeah, it's a common thought. So, sorry. If we're asked to find the derivative of this is kind of a beastly looking thing, and it's. Yeah.
If it's after like the 4th and 5th derivative of something, you start writing the numbers instead of doing the lines.
In parentheses.
Okay.
Yeah. Otherwise, it looks like powers, and it'll help break loose.
Yeah.
Confusion-wise, yeah. So the heavy part of yeah.
What's the difference between the f-1 prime of x and that?
So this part is telling us to take the derivative of an inverse function. Here it's telling us, so you have an inverse function, you must take its derivative. Here it's telling you to take an inverse and substitute it into the derivative of the original function.
Yeah.
So notation-wise, very similar enough to be very confusing, and that's probably why we're starting our journey here. All right, so I'm going to write this a little bit differently. All right, I'm going to write it as f of the inverse. You know, like old school pre-calc, right? Without the prime for now. All right, so that would be the function of its inverse. Now, by the way, before I even go any further, what would that be equal to? If I take a function and compose it with its inverse, so plug the inverse into the original function, what would the result be? I heard elements of correctness. Not one. You wouldn't get f of x, but that's closer to what it would be.
You get
F of 0.
Not 0, not 1. It's not a number.
1 over f of x.
Just x, yeah.
Oh.
That's what
Sine or sine.
when I said I heard elements of it, I thought I heard maybe somebody had. I heard a variable out there, but I wasn't sure if it was.
Well, that kind of makes, so they cancel, I guess.
Exactly. Sine of arc sine of x, for example. It's just x, right? So this is the same idea. It's the same relationship, but this is the precursor to that. All right. So let's take the derivative of both sides of this equation. So I'm going to take the derivative, and actually let me write it a little bit differently. The derivative of both sides, like I said. The left-hand side is going to be infinitely more difficult than the right-hand side, because the right-hand side has a derivative of what?
1.
1. Derivative of x is equal to 1. All right, so if we're looking to invent this rule here, like we accomplished something. I got the 1.
But now you need to find the derivative.
Now I need to find the derivative of this, which seems harder than it is because we don't know anything about the functions themselves, so there really isn't much we can do. We have an outer function. This is f of an inner function that we would normally, if we were writing it all out, we would call it u. So to write the derivative of this, I would say f prime of my inner function by chain rule. Because it's a function inside a function, right? Anytime you have a function inside another function, it's chain rule. Then I would take the derivative of that inner function, this guy right here, so the only thing I could do at this point would be to just say, all right, well, I don't know what the function is, so I'm going to take the derivative of it. Just put a little prime afterwards. You sure can. You sure can. Anytime you don't know what a function is, if you're taking a derivative, you just slap a prime on it and call it a day. But if a function's inside of another function, you have to account for that also.
Can you refresh me? You said it's a chain rule, so you take just the derivative of the entire thing and then the inside?
And then the derivative of the inside. So the derivative of the entire thing with the inside unchanged, so that's this, and then just the derivative on the inside. All right. Now, that's really it, because as, you know, notation heavy as this is, if we move some things around, we have the rule. Because if our goal is to find the derivative of the inverse, that's this part of it right here. So we would get the inverse of x having a derivative equal to 1 over f prime of the inverse of x, etc. All right, so that's the rule. The good news is we just need to know how to use the rule. But it's like, I mean, technically you don't need to know how a hammer is constructed in order to be able to use it, but couldn't hurt, right? I mean, I suppose you don't need to know how electricity works in order to turn on a light switch, but you know, analogies can only go so far. So yeah, there's holes in everything. But I do have the idea that, like, why on earth would we be learning about this if we're not going to see where the formula came from to begin with? All right, so not going to test you on that. I'm going to test you on how to use it, which is really just this last line right here. And that's an adventure in and of itself. But getting a sense of where the formula comes from, I think, is meaningful. And, you know, for those that are actually interested in math, and, you know, you're starting to think, I mean, you're getting college acceptances, you're starting to think about majors and things like that. I mean, pure math is not a common major anymore, but there are majors out there that require elements of pure math in it, and so this stuff could come up over and over again. Right? Engineering, anything involving medicine, you got a lengthy calculus road ahead of you. Yeah, so. Anyway. So let's see how to use it. Should be fun. I like it. You'll learn to love it, I think. And I don't mean that facetiously. I think you will learn to like this approach because it's calculator intensive. I mean, for those of you who are paying attention anyway. It is calculator intensive, meaning pretty much all the work that's necessary to be done can be done on the calculator. So for questions like this, So for questions like this, you can get the answers, the complete answers, without writing anything on the paper except for the answers. All right, so that should be something that you find interesting. All right, so we're given the natural log of x as my function of x. All right, so what we need to do first is find the inverse function at x equals 0. All right, the key to everything is interpreting what that symbolism means. We have this notation. What does it mean? All right, what this is talking about is the x value in the inverse function of f, I'll write of x, is 0. All right, so I'm writing that statement. It's an important statement. All right. It doesn't seem like it would be, but it's incredibly important. It's the key to understanding everything. I'm not overly prone to hyperbole. Never use it. I think it's the worst thing in the history of mankind. The x value in the inverse function of f of x is equal to 0. That's what this notation means. All right. So if we kind of look at it from a different perspective, it also means the y value in the original function f of x is equal to 0. All right, because what is x in inverse world is y in the real world. All right, and vice versa. So x in the real world is y in the inverse world, and y in the real world is x in the inverse world. All right, domain becomes range, range becomes domain. Vertical asymptotes become horizontal asymptotes. The vertical line test becomes the horizontal line test. Roles get reversed. All right, so what that tells me is I don't need to find the inverse of this function. So I'm given f of x equals the natural log of x. I don't need to find the inverse of it. Although we can, this is actually one of the easiest things to find the inverse of. One of the easiest functions in creation. It's actually one of the defining functions. When you're learning about inverse functions, this is one of the first functions they talk about. Does anybody actually happen to know, because I'm saying all this, does anybody actually happen to know what the inverse of the natural log of x is? What did we say? Thought I heard it. E to the x, yeah. So it's exponential e. So you have e to the x looks like this, y equals e to the x. ln of x looks like this. Yeah, you should be, because you're one out of everyone. So a lot of dead air throughout the day after that question. So, but actually it's proving my point, because I'm telling you that we don't need to figure that out in order to get the answer. So it's a sigh of relief for 99% of the population who did not know that the inverse of the natural log of x was e to the x, or at least for this one particular type of problem. All right, how does that help us? Well, they're telling us to find the x value in the inverse function. I don't know the inverse function. Instead, what I'm going to do is I'm going to use this x value in the inverse function as the y value in my ordinary function. And solve. Now, solve, that term, and solve, it could take on a lot of different forms. I'm telling you, this is going to be a calculator-heavy approach. However, you should know that the natural log of meh equals 0. What is meh? Not 0. Right neighborhood, not 0. It's the meh that throws people off. 1. All right. So what's happening here is we're really just proving my point for me, which is great. Calculus, Sir Isaac Newton / Wilhelm Leibniz.
What is the practical application?
Of calculus?
No, specifically, why would you want to flip something like that?
Oh, anytime you have a function that's modeled by an inverse.
And how often do you run into that?
Oh, like all the time. I mean, you can get into like Bezier curves, which are like how cars are constructed.
Okay,
So
so
like,
there is a use for.
oh yeah. Yeah, like all those like parametric curves, which are inverse in nature, or at least parts of them, they like the contours of your cars, they're made by inverse and hyperbolic trig functions. It's like fascinating. And so when you start getting into slopes, like we talk about them as rates of change, that's wonderful. But if you're thinking about how wind would affect a car as it's driving, you would want to know what the slope of the contours of the car would be, right? Otherwise, you're going to have too much friction. It's insanely important. Oh, now I'm interested. Okay, so we're talking about Bezier curves this week. All right, anyway, so ln of x, I can put it into my y1, hit second graph. Now, as long as they're clean numbers, I can get what I need from it. And that's the one thing I'll tell you is I'm going to give you clean numbers because I'm not going to tell you to rely on the calculator and then give you something that's not going to work. All right, so that's important to understand. But anyway, I know that the natural log of x is supposed to equal to 0. Well, that's where the natural log of x is equal to 0. The x value that corresponds with it is equal to 1. All right? So then, we need the derivative of the original function. Also doable. But this is where you start getting into matters of preference. Because if your original function is not something you can find the derivative of, then this technique falls apart. Because you yourself need to be able to find its derivative. Or your calculator is an extension of yourself. By the way, what is the derivative of the natural log of x? What do we say? 1 over x.
Whoa. That's...
All right, so what we got for the first part A, that x equals 1 was our answer. That was f as an inverse of 0 equals 1. That's useful information. Is going to help us in a second. The second part, that derivative, very important also. So what we're going to do is we're going to take our derivative and compose it with the inverse at 0. All right, which seems incredibly difficult until you realize that, yeah, we already figured out that this part is equal to 1. So it's f prime of 1, which would be 1 over 1, which is 1. All right, but now just going back to the calculator for a second here. We went to the calculator initially to find the x value that went along with the y value equal to 4, right? Equal to 0. So that gave us a 1. This got zapped in my right hand because my left hand touched the TV. Yeah, right here is where I got it. Well, not
Sarah found it.
Oh my god!
I don't think it's like invisible leash. No, I thought maybe I had something. But anyway, so in y4, I have the derivative corresponding with the 1. All right, and that derivative is related to the original function. So this work that I did here, I didn't need to do because the calculator gave it to me anyway. So just by typing in the original function, I can get all this information just by going to the table, as long as I have y1 and y4 on. All right, it's just a matter of putting it all together and finding my final answer. And for that, we go back to the formula, because again, the formula is important. If you look at the structure of it, we have the inverse as a derivative at c. So I'm going to write it in this case, inverse is derivative at 0, which would be 1 over the derivative of the inverse at 0. Now, this part B, is the left-hand side of the formula. So whatever we get as the right-hand side is going to be our answer. All right? We just figured out through all of this stuff here, f prime of 1 was equal to 1. That's the bottom of the fraction. So we're looking at 1 over 1, which is equal to 1. All right? So that's the, I think really when you get your practice on this, and we'll do another example in a second. When you get your practice on this, that's the only part that's going to throw people for a loop. If you go through the process, you do the calculator work, you get an answer, you get a number, you just forget that there's a formula involved. And that's the big issue. It's 1 over whatever you get for all this stuff. Right? So it's really the reciprocal of this answer. So as long as you can remember that, you're not going to have any trouble getting these correct. Right? And you know, I mean, this is the natural log of x, which is an easier function to work with than, let's say, the arcsecant of the, you know, the tangent of the natural log of anything. You know, I could just keep saying math terms all day long, but you know, like something really hard. But yeah, it's all going to be following the same progression. So let's see if we could streamline it a little bit, but I mean a lot of it. So arctan of 3x. All right. Step 1. Put in calculator. All right. So step 1, put in calculator. Well, step 1 has always been make sure y4 is in. So that should always be there. You put it in. We put it in like, I don't know, October. And then I told you to never delete it. Some of you have, some of you haven't. Most of you haven't. But there's been some instances where people have loaned their calculators out, and somebody's been really not a good friend and reset it and all that good stuff. So just double check, make sure your y4 is in there. Right?
Wait, Mr. Ken, how do you get the y1 in there? That's the only thing I don't have.
Alpha trace. So if I didn't have this, I would.
Alpha trace.
Alpha trace, and it's the first option.
Oh. Perfect, thank you.
So I'm going to put an arctan, so second tan, which comes up as inverse tan, same thing, or at least the way they calculate it. I'm going to go to my table, so second graph. All right. So part A is asking me, again, in f of x, what is x when y equals 0? So the inverse function of f evaluated for when x is equal to 0 would be what? Zero, yeah. Because all it's saying is find 0 in the y column and get the corresponding value of x. Right? So now the second part, oh, I labeled it 1 for some reason.
I'm confused. Wouldn't it be like, what is y when x equals 0?
That's normally what it would be. But since we're living in the world of inverses, everything's backwards. So in this function, if I were to say find f of 0, I would be saying what is y when x is 0. But because this is an inverse world, x's become y's and y's become x's. So the x in the inverse function is the same as the y in the original function.
Got it.
Can't you just solve the normally and swap them?
You could, unless you can't. Because there are some functions that are what we call non-invertible, which means that no matter how hard you try algebraically, there's no method by which you can come up with an inverse to that function. So you could switch the x with the y, but then after that, you'd hit a roadblock. There would be nothing you could do. Yeah. All right, so it basically makes this not a luxury as much as it is a necessity in some cases. All right, so the right-hand side. So for part B, the left-hand side is what the rule is really asking us to find. The right-hand side is all the, I guess, the meat and potatoes. Like a nice pot roast or something. All right, so this is my rule. somehow we have to reconcile this rule with our work. And really, there's no somehow to it. We've already done all the heavy lifting, right? Because we know that the inverse at 0 is 0, coincidentally. So all I would need is f prime of 0, which is what?
And undefined?
It's 3, yeah.
Oh,
Yeah, because y4 is f prime, right? y4 is our derivative. Because we're looking for the derivative of the original function, f, when the inverse is at 0.
Oh, wow, that's a lot.
It's very weird. The notation is what makes it confusing. But I honestly, I don't know if that's true. I think everything about it is confusing, but the notation doesn't help. How about that? All right.
Mr. Kim, I'm just wondering why my table does not look like
Degree mode versus radian mode should be in radian mode.
that. Does that make a difference?
It would in this case because it's trig.
What is it supposed to be in?
Radian. Oh. All right. So really, what it's coming down to, if you really kind of streamline this, you know, break it down to its base elements. What did we do? We put in the function. We found whatever they were asking to evaluate in our y column, bounced back to the x, and then hopped over to the y4, and then just flipped it, made the 3 into a 1/3. I mean, if I tell you that all you have to do is find this number in your window and then find the y4 value that corresponds to that, I mean, I don't see how that's challenging. But then again, the last component is remembering to flip, remembering that it's 1 over that. That's the thing that people, if they trip up on it, that's where they trip up. All right. Also, you come across something like number 4, where it's like, it's not a clean number. It's not a clean 0 or 2 or something, or even a recognizable decimal. Although, when I was in your place, I recognized this decimal, because I didn't buy into this whole unit circle thing until I got a little bit further down the line and realized that all the stuff my calculus teacher was saying about how important the unit circle was, like, it wasn't, I was where you are. It's not important. It hasn't been important. It only comes up a handful of times. And then all of a sudden it was always important. So then I know. But until I knew, that was 0.8660. That's how I got through every Regents exam. We had to take Regents exams. So when they would say find the sine of 60 degrees, they would have radical 3/2 as a choice. I'd say, okay, I'm sure that came from somewhere. I'd put sine of 60 degrees in my calculator, get 0.8660. And because that happened every other time I put sine of 60 in my calculator, and that always corresponded to radical 3/2, I figured that was probably the right answer. 0.7071, it's a good one, rad 2/2. That always popped out of my mind. So you could do that. Sine of x, 0.8660. All right, well, that's a little iffy. The best you can do, you try anyway, is somewhere in this neighborhood. It's between 1 and 2 for x. You could trace it on the graph. You could do a bunch of different things. You can do an intersect. You could also solve this equation, because again, I know this is the y for the original function. Root 3/2 equals the sine of x. If you know your unit circle, and I already kind of gave it away, x would be equal to what? Right, 60 degrees, but that corresponds to what?
Rad pi/3.
Pi/3, yeah. So that would give me the pi over 3 that I'm looking for. And so that's telling me my answer to part A is pi over 3. And so this is the only way that you can get jammed up on this concept, is that it's like you throw something that's not integer valued related, right? But then for part B, I would find my derivative, f prime of x. Derivative of sine is what?
Arcs.
This is ordinary sine, so it would become cosine. And then evaluate that derivative for my answer to part A. So f prime of pi over 3. Cosine of pi over 3 is? 1/2. All right, and so my answer would be the reciprocal of this. Would be 2. All right.
Would you suggest that we do it that way, or like take the time to like solve it and then like put it in the equation?
See, in this particular situation, because we do know how to find the derivative of an inverse sine function, I would personally find the inverse of this function and then just plug in the radical 3 over 2. I would probably stay away from the rule. Everything else is going to be table friendly, calculator friendly. And in fact, sometimes I just flat out give you the table. Take the calculator out of the equation. It happens every once and again. So, looking at this one here, it's saying h of x is equal to f. Almost at prime, and we're all almost going to say prime at some point. Inverse of f at x. It's saying find h prime of 2. So, well, let's just start off with the notation. It's just really jarring when you look at it. It's funky stuff. But h of x is equal to f as an inverse of x. But I want the derivative. So I'm going to take the derivative of both sides. And then I want to do it at 2. Specifically at 2. So h prime of 2 would be equal to inverse of f evaluated at 2 prime. Which is the rule, or the left-hand side of the rule. And decoding what the rule is asking us or telling us to do is the key ingredient here. And that's really any source of confusion. It's all coming from this notation, once you get down to the ideas behind it. This is saying, again, in f of x, what is x when y equals 2? Question mark. But it's not a graphing calculator question, or at least not directly, because all the information has been given to you. So looking at x against f, so just the first 2 columns. Yeah, exactly. We're just focusing on these 2 guys. I have the y value of 2 corresponds to an x value of 1. So that means I'm looking at 1 over f prime of 1. So what's f prime of 1? So when I have an x value of 1, what is the f prime value that corresponds to that? 3. So 1 over 3. All right. It's not the only time we're going to look at this together, because we do need to really kind of flesh out a little bit more. But that's really it for the unit. We're looking at tests Tuesday, Wednesday next week, something like that. Probably Wednesday if I had to guess right now. But yeah, it's just practice from here on out. So you'll have opportunity to really kind of play around with this and explore. All right. Shortened periods tomorrow and Friday, right? Yes, so plenty of time.